Hello and welcome back. Today we'll be talking about acceleration. Now, acceleration is a funky concept. Why? Because it's often misunderstood in the eyes of the public. When I took Physics 1, I remember thinking acceleration would be simple. I just got my license, of course I know what acceleration is. Well, I was wrong. In the common interpretation, acceleration is just how fast an object speeds up. And that's only a little bit true. The formal definition of acceleration is the rate of change of velocity. Now, that sounds pretty similar to what I said previously, but remember, velocity is both speed and direction. That means acceleration describes the rate of change of an object speeding up, but also slowing down or changing direction, or any combination of those three things. Let's start with average acceleration. Average acceleration is the change in velocity over time, which can also be written this way. This is pretty straightforward and similar to average velocity in its setup. But what about units? With velocity, it was quite simple. Position over time pretty much directly leads to meters per second, a very common velocity unit. But for acceleration, it's meters per second over second. Now what's that? Well, this simplifies to meters per second squared. It's a strange unit and one that will take some getting used to, but I guarantee it will become easy. As we've discovered, velocity is a vector. Since the generalized version of acceleration is velocity over time, acceleration also has to be a vector. Now, why is that? Well, velocity is a vector, and 1 over time is actually just a scalar. And multiplying a scalar by a vector gives us the product of a vector. If that's a confusing topic, I recommend going back to my scalar multiplication video. However, the concept of acceleration being a vector is where a lot of people tend to struggle with the concept of acceleration. Because if it's a vector, that means it needs a direction. In terms of average acceleration, that vector will be the same direction as the velocity vector used to calculate it. But besides that, how can we start visualizing acceleration with a direction? I'm going to start with some simple examples, but believe me, it will get more complex in the future. Let's say an object is moving right and speeding up at a constant rate. If it's speeding up, acceleration is positive and has a constant magnitude. Why is that a constant magnitude? Because it's speeding up at a constant rate. On the other hand, if this object is slowing down, acceleration would actually be negative. In terms of visualizing all of this, the acceleration vector for speeding up would be pointing right. But for slowing down, it would be pointing left. This is a positive acceleration versus a negative acceleration. Now, similar to velocity, we can describe both average and instantaneous acceleration. Instantaneous acceleration is determined by taking the derivative of velocity in terms of time. This also means that acceleration is the second derivative of position, since velocity is the first derivative of position. In this same vein, we can take the integral of acceleration in terms of time and end up with velocity. Now that the bases have been set for acceleration, let's try a couple examples that will hopefully drive home how this funky kinematics concept actually works. Let's say that the Batmobile is driving at 200 miles per hour in a straight line for 1 minute. Well, what's the acceleration here? I'll give you a second to think about that. Well, this is kind of a trick question because there is no acceleration. This Batmobile doesn't change speed or direction for the entire minute, meaning there can't be an acceleration vector. For our next question, let's say that Scooby and the gang are driving down a straight path at 10 meters per second. Suddenly, they see Gramps the Vamp behind them, and Fred floors it. In 5 seconds, the Mystery Machine is now going 20 meters per second. That means, in the course of 5 seconds, the Mystery Machine speeds up from 10 meters per second to 20 meters per second. What's the average acceleration? Well, here we can use delta V over delta T. Delta V is change in velocity, which in this case would be 20 meters per second minus 10 meters per second. Delta T is change in time, and treating the first moment that Fred starts speeding up as time equals 0, delta T is going to be 5 seconds minus 0 seconds. This simplifies into 10 meters per second over 5 seconds, which then turns into 2 meters per second squared. So our average acceleration is 2 meters per second squared. Now, just for the fun of it, let's reverse this scenario and say that Professor Pericles shows up in front of the Mystery Machine, and Fred slams on the brakes, going from 20 meters per second to 10 meters per second in 5 seconds. Let's try calculating average acceleration one more time. Using that same equation, delta V over delta T, delta V is now going to be 10 meters per second minus 20 meters per second, because it is always final minus initial. Our delta T remains the same if we treat the first moment Fred starts braking as time equals 0, so this remains 5 seconds minus 0 seconds. This then turns into negative 10 meters per second over 5 seconds, which then simplifies into negative 2 meters per second squared. This means our average acceleration for the Mystery Machine braking is negative 2 meters per second squared. Now, hopefully this negative acceleration makes sense, because in this scenario, the Mystery Machine is not speeding up, it's actually slowing down, which is what gives us a negative acceleration. Some people like to call this deceleration, but I tend to just call it negative acceleration. But if you do see the word deceleration anywhere, just know it is negative acceleration. Let's try another example. Let's say we have a position function of x of t equals 11t squared plus 2t plus 2. Let's try and find acceleration at time t. To do this, we need to take the double derivative of this position equation. So, let's take the first derivative, and that ends up as 22t plus 2. Now, what is this equation that we've just found? Well, this is actually velocity. But we're not here for velocity. We want acceleration. So we need to take the derivative one more time. And doing that gives us just 22. Now we're going to end off with a pretty difficult problem, so buckle up. Given an acceleration function, a of t equals 2t minus 8, initial position at 2 meters, and initial velocity at 1 meters per second, find position after 3 seconds. Well, the first thing we have to do is take the integral of our acceleration function. So, take the integral of acceleration in terms of time, and that ends up with t squared minus 8t plus c. Now, this plus c cannot remain because we have to take another integral. So, how do we get rid of it? Well, we can use one of our givens. We are aware that initial velocity is 1 meters per second. Let's plug in time 0 into our new velocity equation. This ends up giving us just v of 0 is c. And since we know v of 0 is actually 1 meters per second, c is also 1 meters per second. This gives us a final velocity equation of t squared minus 8t plus 1. Now to get position, we need to take the integral of this velocity function. So, taking the integral in terms of time gives us 1/3 t cubed minus 4t squared plus t plus c. Now we need to get rid of c one more time, and to do this we can use the last of our givens, which is initial position at 2 meters. Let's plug in 0 into our new position equation. This gives us an initial position as being equal to c. And since we know initial position, we can see that c is 2 meters. This gives us a final position equation as 1/3 t cubed minus 4t squared plus t plus 2. Now for the last step of this problem. We want the position after 3 seconds. So to do that, we can just plug in 3 as t into our equation. And this eventually gets us to negative 22 meters, which is our final answer of the position at time 3. Thank you for watching, and I hope this was informative. If you want more of this, consider subscribing or donating to the Patreon. Happy learning!